If China's export ban on rare earth elements holds for 18 months, the United States Air Force's most expensive weapons program in history could face a production halt it has no approved domestic fix for. That program is the F-35 Lightning, and the component at the center of this crisis weighs less than a kilogram, but cannot be replaced by anything currently made on American soil. The April 2025 export controls that Beijing imposed cover a category of materials called heavy rare earth elements. Think of these as the ingredients list for the most powerful permanent magnets ever engineered. Without them, you cannot build the actuators that move the F-35's control surfaces, the motors inside its targeting pods, or the precision drive systems woven through dozens of other weapons platforms. The controls did not arrive without warning. China produces roughly 90% of the world's refined rare earth output and has been signaling for years that this leverage exists. What changed in April 2025 was that Beijing converted the signal into policy, requiring export licenses for specific rare earth compounds and magnet intermediates, a licensing regime that in practice functions as a near-total pause on shipments. To understand why this particular ban bites so hard, you need to understand what makes these magnets irreplaceable. A neodymium iron-boron magnet, the dominant type, generates a magnetic field roughly 15 times stronger than a conventional ferrite magnet of the same size. In aerospace applications, where every gram of weight and every cubic centimeter of volume is contested, that ratio is the difference between a design that fits inside the airframe and one that does not. Adding a small percentage of dysprosium to the alloy pushes the magnet's operating temperature high enough to survive the heat generated inside a jet engine bay. That additive, dysprosium, is precisely the element most tightly controlled under the April 2025 rules. Without it, a neodymium magnet loses its properties at temperatures the F-35's internal systems routinely exceed. The F-35 is not the only platform at risk. The same magnet chemistry appears in the AIM-120 air-to-air missile, in the Joint Direct Attack Munitions guidance kits that turn unguided bombs into precision weapons, and in the electric drive systems of Virginia-class submarines. The ban does not target one aircraft. It targets the underlying physics that modern American weapons depend on. So how did the world's most powerful military end up so exposed? The answer is a procurement logic that prioritized unit cost and performance over supply chain resilience. When Lockheed Martin and its subcontractors sourced magnet assemblies through the 1990s and 2000s, Chinese suppliers offered consistent quality at prices no Western producer could match. Sourcing decisions made quietly by mid-level supply chain managers compounded into a structural dependency. The rare earth supply chain is not a single link. It is a chain of 5 distinct industrial steps. Mining the ore is step 1. Separating the rare earth oxides from the ore is step 2. Reducing those oxides into pure metal is step 3. Alloying the metal with iron and boron is step 4. Sintering and magnetizing the finished magnet is step 5. China dominates all 5 steps for the heavy rare earths. Western investment largely stalled after step 1. MP Materials in California mines and partially processes rare earth concentrate at Mountain Pass, the largest rare earth deposit in North America. For years, the company shipped that concentrate to China for finishing because no viable domestic processing chain existed. It has since moved to build out downstream capacity, but as of the spring of 2025, it cannot produce the sintered dysprosium-doped magnets that defense contracts specify. The Pentagon is aware of the gap. The Department of Defense has issued funding notices under the Defense Production Act to accelerate magnet manufacturing inside the United States. But standing up a qualified production line for a defense-grade sintered magnet is not a matter of months. Qualification testing, quality audits, and the engineering of the full sintering process from scratch take years under normal procurement timelines. One proposed bridge is stockpiling, buying and storing magnets and magnet assemblies before the export license regime tightens further. The Department of Defense has authority under the National Defense Stockpile to do exactly that. But the stockpile program has been chronically underfunded for 2 decades, and rebuilding it for a material as process-specific as a sintered defense magnet is expensive and slow. Allies complicate the picture in both directions. Japan's TDK and Shin-Etsu Chemical are world-class producers of sintered neodymium magnets and are not subject to China's export controls on their own production. The problem is that their output is largely committed to consumer electronics and automotive customers. Redirecting Japanese magnet capacity toward American defense needs requires renegotiating existing supply contracts. And that takes diplomatic and commercial leverage that does not arrive quickly. There is a deeper redesign argument circulating inside defense research circles. Could next-generation systems be engineered around magnet types that do not depend on heavy rare earths at all? Some actuator functions can, in principle, be handled by high-temperature superconducting coils or by certain ferrite arrangements. But retrofitting those into existing certified airframes like the F-35 is not an engineering option. It would require a new design program, measured in billions of dollars and at least a decade of development. The export controls also carry a secondary effect that rarely makes headlines. Defense primes must certify every component in a qualified weapons system. Swapping a Chinese-sourced magnet assembly for one from a new domestic supplier does not simply require buying a different part. It triggers a requalification process governed by mil-spec standards. That process can run 18 months to 3 years, even when the replacement part tests identically on every metric. This requalification timeline is where the 18-month estimate in the opening becomes lethal. If a production halt stretches past the point where existing certified component inventory runs out, the line does not simply slow down, it stops. And a stopped F-35 line does not restart in weeks. The tooling, the workforce sequencing, and the supplier synchronization that a modern fighter program demands take months to reassemble, even when every part is theoretically available. The geopolitical timing is not accidental. China imposed these controls during a period of sustained trade friction with the United States over semiconductor export rules. Beijing has watched Washington restrict its access to advanced chip-making equipment, and the rare earth move is a calibrated response, applying pressure at a point where American vulnerability is genuine and the domestic remedy is years away from maturity. The leverage is real because the dependency is real. In 2010, China briefly restricted rare earth exports to Japan during a diplomatic dispute over a fishing trawler incident near the Senkaku Islands. Japanese manufacturers scrambled, prices for rare earth oxides spiked by a factor of 10 within months, and the episode produced a wave of strategic investment in alternative suppliers. That investment partly faded when prices normalized. The lesson from 2010 was learned and then quietly forgotten. The parallel that defense analysts now cite is the gallium and germanium export controls Beijing activated in the summer of 2023. Those materials feed into semiconductor fabrication and compound semiconductor devices. The restrictions produced short-term price volatility and some production disruption, but the world adapted, partly because gallium and germanium have more distributed global sources than the heavy rare earths do. Dysprosium and terbium have no equivalent safety valve. What would a genuine domestic solution actually require? Mining reform to fast-track permitting at identified rare earth deposits, federal capital for separation and alloying facilities, long-term government offtake agreements large enough to justify building magnet sintering plants at defense-relevant scale, and patience, because none of this compresses below a 5 to 7 year window, even under optimal policy conditions. The United States is not at year 0 of this effort, but it is well short of year 5. In the near term, the most plausible mitigation is a combination of accelerated allied sourcing from Japan and Australia, targeted stockpile purchases, and quiet diplomatic negotiation for limited license exemptions from Beijing, the kind of back-channel arrangement that neither government publicly acknowledges. None of these options removes the underlying dependency. They buy time, and what happens in that time will determine whether the United States treats rare earths as a national security priority or reverts to the cheaper, easier default of offshore sourcing once prices normalize again. The F-35 is often described as the most sophisticated warplane ever built. That description is accurate. What it leaves out is that the sophistication depends on a supply chain that runs through a country the United States now formally considers a strategic competitor. The magnet inside the actuator inside the jet is not a footnote to that rivalry. It is one of its sharpest edges. The April 2025 export controls may tighten further, be rolled back in a trade negotiation, or settle into a permanent friction that neither side fully resolves. What will not change is the underlying physics. As long as the most powerful compact magnets require dysprosium and terbium, and as long as those elements flow overwhelmingly through Chinese processing infrastructure, every advanced weapons program in the Western Alliance carries a vulnerability that no procurement directive has yet closed.